So welcome to this last lecture of the year in Strength of Materials 1. So I have received a few requests for repetition exercises, so exactly 3, and that's about what I can make, I think, here in this lecture, so that fits very well. Also, it covers more or less all of the year's syllabus, so that fits also very well. Before we get to that, let me just say a few words about the evaluation. So not much to note. I think, we had about a little bit more than 50% participating, which is okay, I think, to get a representative outlook of how the course has been perceived. So we are in the quite positive answers. I think we're with a few negative outliers, but I think that overall I'm pretty satisfied with the response. So one of the important things, I guess, is this one. It looks like most people attending the course think that they have learned a lot from the course, and I think that's the most important thing. Yes, and this is also pretty positive. So I think in terms of the comments, I think there are not many comments. There is 1 or 2 comments about TA session or TA needed for the exercises. I don't really follow this. I think I have had actually plenty of time, not that many questions in the problem session. So I'm a little bit surprised of this comment. So of course it would have been nice here to get some more feedback on what is meant here. But I think there has been plenty of time for me to answer all questions, and I could also ask or answer more questions. So I don't think time has been a limiting factor here. And also comments to me are also very good, so I'm also happy about that. So no more comments about the course evaluation, so we will go straight to the exercises. So, as I said, 3 problems have been mentioned, and in some of the problems it's only been one of few questions that have been asked for, but I think in order to get the complete picture of a problem, I think we will do all of the 3 problems that have been asked about. So the first one is a pure statics exercise. There are 5 questions in this one, so we will go through all of them. The second problem is a problem about a distributed load and about drawing stress resultants. And the final problem is a problem about the composites. So as I said, that covers pretty well a lot of the syllabus that we have been going through in the course. In the first question, we are asked to determine the support reactions at point A and B when the mass small m is equal to 0. So we see here a drawing of the problem. So small m in the first part is equal to 0, but we have 2 other loads. We have capital M here and we have capital M here. So we have 2 external loads on the system, and so we're asked to determine the support reactions at the 2 points of the support here and here. So of course, when we're asked about support reactions, statics exercise, we need to do a free body diagram of the complete structure. So let's move to it. Support reactions in A and B. So we will draw a free body diagram. So we have one external mass here. We have another external mass in the middle here. And then we have some structure, of course. And I'm just going to be slightly sloppy in drawing this one. And why am I going to just allow myself to be slightly sloppy with the rest of the structure? Because we have, when we're drawing a free body diagram of the entire structure, we need only external loads. So what do we have of external loads? Of course, we have the support reactions in A and B, which we are asked to compute. And we are told also in the exercise that we have no friction, so we only have vertical support reactions at the 2 points where the whole crane is. So I'm going to call them AY and BY. And then we of course have the external loads coming from the 2 big masses loaded on the crane. So we have here MG and MG. And that's it. Since our small m is equal to 0, we don't have any external loads from this small mass. And also all other forces in this complicated crane structure, they will be internal forces, right? So they should not be drawn on a free body diagram of the complete structure. So it's really a good idea to be careful about drawing these forces so that we can see where they act and in which direction. I think this drawing where the forces are placed are almost on the limit of being a little bit too sloppy, right? So really please make sure that you make the drawing very clear so everybody can see where the forces are located. And please make sure that you do not draw any internal forces in the free body diagram of the complete structure. Okay, so now we have the free body diagram. We can start doing equilibrium equations. And as usual, when we have 2D statics, we have 3 equilibrium equations at our disposal. So we can start with force equilibrium, we can start with moment equilibrium, we can do one or more moment equilibria, and we can combine these equations the way we want. So of course it's smart to choose equations that will make your calculations as easy as possible. So here I will choose to do a moment equilibrium around point A. So I indicate this with a round arrow here and a arrow indicating that we compute our moment in the positive direction anti-clockwise. And I just put the A in here so we can see that we do a moment equilibrium around A. It's not called momentum, and it's not momentum in one point or something like that. I still see that formulation being used. It's moment equilibrium around a point. Okay, so how do we compute the moments? Well, we have to identify which of the external forces gives a moment around this point. And we of course have By, and we can see By gives rise to a positive moment around A, moment anti-clockwise. So we have the force and we need the moment arm. And when we look at the drawing, we can see that the moment arm, so the distance between the A and B point, is 4 meters. Yes. And we can see that the middle force or the middle external mass also gives a moment around point A, and it's in the positive direction. So M times G. And the moment arm to this external force is 2 meters. It's an equilibrium equation, so the sum of these two moments has to be equal to 0. This equation we can easily solve for By. And we get 1/2 times capital M times G. And we can of course insert the numbers if we want to. Okay, so now we have one of the support reactions, and now we need to the other one. So of course now we can start doing vertical force equilibria. We could also take the moment around point B. If we do that, we can see here that AY gives a negative moment. And then we have both external forces, both big masses, providing a moment around point B. They're both in the positive direction. First, we take the one farthest away from point B, has also the moment arm 4 meters. And we have the other one with a moment arm of 2 meters. It's a moment equilibrium. Sum of moments has to be equal to 0. And again, we can solve this equation for AY. And in this way, we find that AY equals 3 divided by 2 times capital M times G. Now for problem B, we are now asked to determine how large the object mass small m can be before the crane tips. So we're actually given sort of a help to this, because it is indicated that that mass corresponds to the point where we get the 0 reaction force in A. Okay, so we have to do another free body diagram and more equilibrium conditions. So let's take a look at it. Now we have the second free body diagram here, but we have to modify the one. I've copied it from part exercise A, but we have to modify this free body diagram to fit the new conditions. So we're now asked for the value of small m. So we have now another external force coming from the small mass, mg. But we're now also told that the point where the crane tips is actually exactly the point where we don't have any normal force in A. That's where the wheel starts to come off the ground. Then we don't have any external or any support reactions in A. So before we set up the equilibrium equations for this problem, there's one very important note here. Do not be tempted to use the same value for By as we have computed in A, right? Because we have a new system now. We have other forces. We have the small mass added. Ay is gone. So the By that we compute in B will not be the same as the By that we computed in A, right? So that's a very important notice. Of course, if we choose our equilibrium equation as the moment equilibrium around point B, we will not use By anyway. But you might have chosen other equilibrium equations where you have used By, so there the note should be taken. So, moment equilibrium around point B. Well, now we have the small mass. If you look at the drawing, then the moment arm to the small mass is 11 meters. And then we have the two big masses again providing a moment. One with the moment arm 4 meters, and the other one with a moment arm 2 meters. Solve this equation for small m, which we're asked for. We get that small m in this case becomes 6 divided by 11 capital M. Now in problem C, we're asked to compute the force in the cable from I to G in the specific case where the mass is exactly what we computed in question B. So now it's important to realize that the force in the cable IG, it's an internal force. So we can no longer restrict ourselves to looking at the complete structure. We either have to split up the structure in parts or we have to make cuts. And splitting up the system in parts here, there's no, you can say, cookbook of how to choose the system that we now look at. So you have to think about where would it make sense. So of course we need to look at a part of the structure that's located where we have the force IG we need that. So one obvious choice could be to look at the part of the structure composed of the beam from F to G to H. So this part. So we take this part of the structure out of the complete structure, and then we of course have to make sure that we draw all external forces on this part. So the forces that were internal forces for the complete structure now becomes external forces to the parts of the structure. So now I made a couple of drawings here, and the first one, if we concentrate on that one, we now have the part of the structure going from F to G, and then to point H over here, right? We have already now drawn the external force coming from the small mass, and as was specified in the exercise, we needed to use that specific value that we computed in exercise B, so it's 6 divided by 11, capital M times G. And now we have to draw the external forces coming from the other parts of the structure. So first thing we can do is draw our cable force. Now the arrows become not so straight as they could. So this is IG. And when we look at the picture of the structure, we can see there is a rod going from I to F. So in a rod, of course, we also know that we have a force in the direction of the rod. Which we call IF. And then we also have this part of the structure connected to the vertical beam going from D over E to F. And it's connected also in the pin, so of course we can get two perpendicular forces coming from the lower beam. So we can call those F, Y, and Fx. Now, the first thought here when you have drawn this free body diagram of the part is that that was not maybe a good idea. You have too many unknowns, right? How many unknowns do we have? Well, we have 4. We have Fx, we have Fy, we have If, and then we have Ig, which we want to determine. But it's not necessarily a problem to have too many unknowns if we can get rid of many of them by a clever chosen, for instance, moment equilibrium. Then we can actually compute some of the forces. That we cannot compute all of them since we have 4 unknowns and we only have 3 equations. But as we can see, if we choose to take moment equilibrium around point F, well then 3 of the unknowns, If, Fx, and Fy, do not enter into this moment equilibrium equation, and we can use this to determine Ig directly. So this is the force, and then we have the moment arm. So the moment arm is 12 meters. And then we have the contribution from the cable force, Ig. So it's been a while ago since we did this type of static calculations. The most easy way to compute the moment of Ig is to split up Ig into the vertical and the horizontal components and take the moment contribution from each of the components separately. And that's why we have drawn down here a small helping drawing in order to get the components, the vertical and the horizontal components of the force. So what is needed is the cosine and sine terms here. So I have indicated the corresponding lengths, which we find from the drawing, which is 2 in the vertical direction, 8 in the horizontal direction, the distances between I and G. Then we can compute the other quantities, and we can compute the cosine and the sine components of this in this triangle. So as said, we need the vertical component here first. And it gives a positive moment. So we say Ig, which is the force itself, and then we want the vertical component. And the vertical component, well, it's the small component of the two. If you don't remember if it's sine or cosine, well, you can always at least for some angles, you can easily identify if you want the big or the small component. And the vertical component is here the small one. So it's definitely sine, which is 1 divided by square root of 17. And then we need the moment arm. And the moment arm is 6 meters. So the horizontal component of the force Ig goes directly through point F, so it does not give a moment around this point. Now this we can use to compute Ig. And we get that if we collect all the terms here, that the force Ig becomes 12 multiplied by square root of 17 divided by 11 multiplied by m and multiplied by g. Now if we now go to point D, we can see that the next thing for us to compute is the force in the bar IF for the mass found in question B. So we are up there again looking at the top part of the structure. But as we saw from the previous calculations for the system FGH that we considered in problem C, we had 4 unknowns. So I think it's unlikely that we can find our force IF from the same system. So what we will do instead is looking at the point. Remember when we did the truss exercises, we could also have the method of joints, which is actually a point equilibrium. So even this, though this is not a truss structure, if we have a point or joint, we can still make the equilibrium of a point here. So looking at point I is actually going to give us enough information to find the force IF. So let's look at it. Let's draw up our point I here. So we have 3 forces going acting on that point. We have the vertical force IC. We have the Ig that we just computed, and then we have the IF, which is the one that we wish to find. So when we look at equilibrium for a point, we only have 2 equilibrium conditions. And so what we will choose here, well, if we look at a horizontal force equilibrium, then we can see that the IC does not contribute, and then we have only one unknown, and that is the IF that we wish to compute. So let's see, we have Ig. So now we need the horizontal force component from Ig, and we already computed the cosine alpha, so we will have 4 divided by square root of 17 as the horizontal component of Ig. So if we look at the drawing from IF, we can see that the bar IF is at a 45-degree angle. That means that the components are particularly easy, square root of 2 divided by 2. So that's one of the things that are, one of the quantities that are good to remember, that is good to remember is the components for a 45-degree angle, square root of 2 divided by 2. So the sum of these 2 forces must be equal to 0, and we can use that to compute IF. So we will get IF equal to minus, and then we will get 8 divided by square root of 34 multiplied by Ig, which was 12 square root of 17 divided by 11 mg, like this. And this, of course, can be simplified. So we get minus, and the minus comes in because, of course, in IF, which we can imagine a little bit, we will have a compressive force in that rod. So we will have a negative force. That's always the case when we draw the forces away from the joints. We get, when it's negative, we get a compressive force in the rod. So we get 96 divided by 11, and then square root of 2, and then mg, like this. And so the final exercise is exercise E, and that's about determining the buckling load for bar IF. And that's of course relevant because as we just computed, IF is subjected to a compressive load, and bars are very strong in tension and compression, but the limiting factor is buckling when we have compression, right? So at some point, IF, if the load is too big, then IF will buckle. So it is not a difficult exercise because, well, we only have a limited number of buckling cases depending on the boundary conditions. And if we see at the bar IF, it has a simple hinge in both ends. So we can directly identify. So we will have buckling case 2 by identifying boundary conditions and then just simply inserting from the formula. We know that for case 2, the buckling load will be pi squared multiplied by EI divided by L squared. So after computing the moment of inertia for the corresponding cross-section and computing the length of that rod, we can simply insert P critical. So it's very simple in that respect. So in the next exercise, X03, we have a cantilever beam, which means that it's fixed clamped in point A, and then it's free in point C. And then we have a distributed load starting at point B, linearly increasing up until point C, with the total load, the total force of that distributed load is capital Q, pointing upwards, as we see from the small arrows. So the first one is sort of a helping exercise, where we are asked to write an expression for the force intensity Q of X. So there are two things to this. First of all, it's a bit troubled by the fact that we are provided the total force Q instead of small q. And then we also need to take into account that when we specify the force intensity, we specify it downwards. So here we have a force upwards. So a few things we have to remember when we write up this formula. So let's look at it. So here we have it. So let's just look at how do we relate capital Q to the intensity at the endpoint. That's usually how we specify, and that's a good help in order to specify the intensity distribution is to have the value of the small q at the end. We usually call this Q0, right? And we know that, so capital Q is total force. So how do we first relate small Q0 to capital Q? Well, we know that the total force is equal to 1/2 intensity at the end and then multiplied by the length. And here, of course, we should be a little careful because the distributed load is only acting on 1/2 of the length of the total beam, so the corresponding length is L/2, right? And then our Q0 is, well, we want that to be negative, right? We always specify the direction of the small q's as being downwards, so we will have minus here, right? So Q0 we can find as 4Q minus divided by L. Now then we can move on to drawing or to specifying the distribution of the load along the length. So our x coordinate is going from here so when we specify the intensity along the length, well, for the first part of the beam, of course, we have no intensity, right? So going from 0 to L/2, we have 0 intensity. And then we have to specify the expression for Q of X so that it matches with the expression that we have for the total force and the force intensity at the end of the beam. Well, we know that it's a linear distribution and it should be 0 when we are at x equal to L/2, right? So there are many ways of constructing this. I think a little bit of trial and error is maybe the most easy thing because we know we have a linear function. We know it should be 0 when we are at x equal to L half. So we could start by making this parenthesis that we know is equal to 0 when x is equal to L divided by 2. And then we know that when x is equal to L, then this value should be equal to Q0, right? So specifying 2Q0 here means that when x is then equal to L half, then we get Q0. And that is valid for x going between L half and L. Of course, we can then insert capital Q, which we should. So when we insert capital Q, we get minus sorry, that was a mistake. So not 2Q, but 8Q, of course. Like this. Now, in the second part of the exercise, we're asked to determine the stress resultants, N of x, the normal force, V of x, the shear force or transverse force, and M of x, the moment along the whole beam, and also to draw the corresponding diagrams. So here we have two parts in this beam, right? We have the part from A to B, where we have no distributed load, and we have the part from B to C, where we have a distributed load. So we need to handle those two parts individually or separately. Now looking at the first cut, we make that to the left of point B. So we are now restricted to look at the first part of the beam. We make a corresponding, what we call the cut 1, at a point X, which is of course arbitrary, the point X, but it's located in between point A and point B somewhere. Now, in order to represent the distributed load, we have here indicated the corresponding force. We know it's Q, capital Q, we've already been told that, but the location, the equivalent force center for this distributed load, we have already computed that several times, and we know it's in the 2/3 point, or 1/3, depending from which side you look at it. And for this particular, this particular distribution, we can then identify the distance between the equivalent force and the endpoint as being L divided by 6. Now, one thing we know immediately, because we have no normal forces in the structure, so we can already write up N of x is equal to 0. And that we will have also for the other part of the beam. So I will not even draw the normal force on the force diagram because it's 0. Because it just, becomes a little bit messy. So we have the moment, M of x, and we have the shear force, V of x. Remember, it's essential that you use the sign convention for these stress resultants. Okay, now in order to determine V of x of M of x, we can make equilibrium equations just as a normal statics exercise here, right? So the most easy one to start with is, of course, vertical force equilibrium. So we have V of x plus Q is equal to 0. So we know that V of x will be minus Q. So it's a constant from A to B, our shear force, and it has the value minus Q. Now looking at the moment distribution, of course, the most easy thing to do is to take a moment equilibrium around point X. So we can see our moment contributes, the moment that we're trying to compute, M of x. V of x does not contribute, but Q contributes, of course. And the Q contributes with the moment that we just need to be a little bit careful of computing the moment arm from X until up till the point Q. So so what we can see here is that the distance between capital Q and point X will be 5L divided by 6, because our force Q is located, the position L divided by 6 from the endpoint, and then minus X. Like this. And the sum of these moments is equal to 0. So that means that we can write up our moment simply as Q 5L divided by 6 minus X. Now for the second part of the structure, we have to be a little bit careful. We could do the same as we did before, but actually when we make the cut, as we could say a cut to somewhere in the middle, somewhere along the second part of the beam from B to C, then we also have to find the equivalence force center for the remaining part of the distributed load. We could do that, and it's also possible, but always remember there's another way of finding the stress resultants when we have a distributed load, and that's by integrating the load distribution. So let's try that. I'm not saying it's easier here, but it's doable, and it's not more difficult than finding the equivalent force center. So let's remind yourself that you have the expressions for V of X and M of X. So it's minus Q, and then we have a constant, and then when we find the moment, it is the integral of V of X plus C2. And then we of course find the two constants C1 and C2 by applying the boundary conditions. So these are completely general formulas. They could also be used if Q is 0. So we could also have used that method from the first part, from A to B. But there it was definitely easier to use the direct statics approach. But in this case, it might be easier to use this approach. So we need to insert our distributed load. So our V of X becomes, we insert the value that we just computed for Q of X, and with a minus, so the minus goes out the first minus, and then we had a constant, which was 8 capital Q divided by, so we found our distributed load here. I just realized that I did a small mistake because I was missing a part divided by L here, which then translates into L squared here. So that's in order to make this work. When you insert X equal to L, then we of course need to divide by L in order to get the Q0. Small mistake, but let's insert this value here. So we get L squared here. So the minus is taken away from the other minus, and then we have the part that needs to be integrated. So it's X minus L divided by 2 dx, and then we have the constant. So doing the integration is quite simple here. We get 8 capital Q L squared, and then we get 1/2 X squared minus L divided by 2 times X plus C1. So let's see if we can find our constant C1 from the boundary conditions. Well, what do we know? Well, at X equal to 0, this whole exercise is only valid from X equal to L half, right? That's where we have the distributed load. But fortunately, we have the boundary conditions for X equal to L because we have a free end. Even though we have a distributed load going all the way to L, doesn't mean that the shear force is not 0 at the free end. It is only if we have a concentrated load at the free end, it's not equal to 0. So that's important. You might be confused by the fact that we have a distributed load there, but we still have a free end. So our shear force at x equal to L is equal to 0. So by inserting, we get AQ L squared 1/2 L squared minus 1/2 L squared plus C1. So the first part is 0 anyway, so we actually, for this to be true, need that the C1 constant is equal to 0. Okay, so we can write up our distribution of our shear force as, well, we can simplify the expression a little bit, so we get, draw out 1/2 from the parenthesis, so we get 4Q divided by L squared, and then we can have an X here, and we get X minus L divided by 2. So now we can go on to the second part, which is finding the moment distribution. So here we need to integrate the second part. So we need to integrate v of x, and we also have a constant here. And then we integrate this x squared minus L half x. Oh, sorry. I can see here I made yet another mistake. This is not L half. This is L. Sorry about that. And that also goes down to this one. So here I have x L. Well, and then we get the second constant. So let's integrate. Get 4Q L squared. Get 1/3 x to the power 3 minus 1/2 L x squared plus the second constant. In the same way as for the shear force, we know that in the free end we have a 0 moment. So we know that the moment of x equal to L equals to 0. So we insert to 0, which means that our C2 can be found as 2/3 Q multiplied by L, which means that our moment distribution, putting everything together, becomes 4Q L squared minus 1/2 L x squared, and then plus 2/3 QL. Of course, this expression can be put in a different form, but it's not decisive. This is a valid expression, and anyway, we're asked to draw the distribution, so let's do that as well. Now, if we look at the answer from the first part, from x going from A to B, we saw here that our v was equal to minus q, and our m of x is a linear decreasing function starting with the value 5L divided by 6 times q, and then decreasing linearly until we reach L divided by 2. So we can draw this. The first part here. And then we said we had 5, 6 q of L. And then we have a linearly decreasing function. So we don't have any concentrated loads in this case. We have no concentrated loads, so we have no concentrated moments. That means that we do not expect any discontinuities in terms of either the shear force or the moment. So, and we could of course check that in the expressions. And indeed, in the expressions that we derived just here, we could see that the shear force at x equal to L divided by 2, if we insert that, that matches exactly minus q. What we can see here now is that if we look at the shear force, it's a quadratic function in x. And if we draw that, we know it has to end at 0 for x equal to L, and the quadratic function will, in this case, look like this. So it goes to 0 at x equal to L. For our moment, again, we expect the value here at the end here, if for x equal to L divided by 2, it matches what we had from the other case, so that we have a continuous curve. And then we see here that we have a cubic function, and inserting specifically the cubic function here, we will find that the follows a curve sort of like this. It's not easy to see that it's a cubic function, but it is. Okay. Of course, with the aid of some mathematical software, this is easier to make a nice drawing here. The final exercise is a composite beam. So we're given like an eye profile, and well, it's maybe a little bit more complex when you look at it than some of the other composite beams. So that means that we look at the cross section here. We have two parts to it. So we have the light gray, which is a softer material. We have the darker gray, which is a stiffer material. But it's not just given the Young's modulus, because we know that both of these parts are fiber reinforced materials. But we are giving the percentage of the fiber reinforcement in the two parts, so we can use the formulas for the fiber reinforcement that we have, the rule of mixtures, in order to compute E1 and E2 for the corresponding parts of the cross section. So when you just look at it, it might look complicated, but it's actually not too bad. So we have an E1 in the bottom part, the stiff part. We have an E2 in the top part. So using the rule of mixtures, we are told that in the stiff part we have 50% of matrix material, 50% of fiber reinforcement. That means that the corresponding Young's modulus simply 0.5 times E fiber plus 0.5 times E matrix. And then with the given numbers, that corresponds to 18 times E matrix. In the softer part, we know we have only 20% of fiber material. That means that the corresponding numbers will look like this. 7.8. So what it tells us is that we have a stiffer material, which is a bit like 2.5 times stiffer than the softer material in this part. So you can say that this is a extra small exercise before we get started to actually find E1 and E2 from this fiber reinforcement specification. Now, the first exercise that we need to do is more traditional in terms of composite beams. We are asked to find the neutral axis, and that's of course because we can see that it's not a symmetrical cross-section in respect to the distribution of stiffness. So we do not in advance know where the neutral axis is. So once we have found the beam neutral axis, we can then use it to find the bending stiffness, which is this H3 star, which is the main quantity when we're talking about computing composites. It's finding H3 star, which is the equivalent bending stiffness for composites, right? So instead of having EI, the bending stiffness for a homogeneous beam, we are finding H3 star, which is the bending stiffness for a composite. So doing that, there is a very strict cookbook in order to being able to find that. So the first part is actually, sometimes you overlook the importance of it. It's critical that you understand that when we compute the neutral axis, the position of the neutral axis, we can put in a coordinate system in any way we like, right? So, of course, the computations that will be involved are very dependent on where you put this coordinate system, but the results is, of course, independent of that. So in this exercise, we simply choose to perform all of our to make all of our computations based on a coordinate system with the origin in the neutral, in the center point, in the symmetry point here. And we could have chosen another coordinate system. And once we have determined or specified this coordinate system, we simply compute the necessary quantities. And the necessary quantities are first computing h1, and h1 is given as e1. Well, the computation, that's an integral, but it comes specifically simple when you have a constant Young's modulus in the various parts. And here we have a constant Young's modulus, so we don't need to do the integration. It just becomes the Young's modulus multiplied by the corresponding area. So the area where we have the Young's modulus equal to E1, when we look at the geometry, is 3a squared. That's the area of the bottom part. And then we need to add that part that has Young's modulus 2, and the corresponding area of that part is 5a squared. But remember, if e had been a varying function of z, then we had needed to do the integration. Well, but this we can compute easily, and we get 93 em a squared. This is the first part. Second part is our h2. And our h2 is an integral. So here we are computing our integral where we have e1, but then we need the set, and we need dA. So we are integrating over the area, again, where we have e1, but we need to include the set coordinate in our integration, so that's why we need to integrate here. And we need to do the same where we have our e2. Now let's look at the specific integrals that are involved here. Okay, so, and we're of course integrating with respect to set. Now, actually, the first part where we are integrating in the bottom part, where our Young's modulus is equal to E1, is the easiest part, because there we have a constant width, right? So we are integrating, and our set goes, in this case, from A to 2A, right? This is based on our choice of coordinate system for the calculations. We have E1, we have set, and now we're splitting up. So this is an area integral, but our width is constant in the bottom part. So our width is equal to 3a in the bottom part. And then it becomes d set, right? So that's splitting up the dA integration into a d set integration by realizing that we have a constant width. So this would have been more complicated, of course, if we had a triangle or something like that, where we needed to specify the width as a function of set. We don't need to do that. Now the second part, we need to split that up in two, because we don't have a constant width all along that part. So we take the first part. We have E2, we have set. So the first part has the width 3a, just as the bottom part d set. And but that's only integrating from minus minus 2a to minus a. There is, note here, there's a small misprint in the solutions. That should be corrected. So the integrals boundaries are here a little bit wrong. Okay, so it's from minus 2a to a. And then, of course, we need the second part of the integral. Still E2, it's still set, but the width of the middle part is only a d set. And that integral goes then, of course, from minus a and then to a. And doing this whole computation, we get 45.9 em a cubed. And there's also a small misprint. It's not a minus as it's in the solution. Okay, but now centroid or neutral axis is determined just from these two numbers, h1 and h2. We get set c equal to h2 divided by h1, and the answer is 0.4935a, right? So of course, due to the stiffer lower part, the E1, our beam neutral axis or centroid is or elastic centroid is located further down than our choice of our set coordinate, right? So it's, well, we cannot exactly see where, but it's, well, maybe close to this line here where we have the beam neutral axis. Well, so this is the first part. If we don't know the centroid, we need to compute it. So we can then go on to compute H3 star, or the bending stiffness for the composite. Just a note, we also have the H1 star and the H2 star. So what are the importance of those? Well, H1 star is always equal to H1 if we need to compute H1 star. And H1 star is the actual stiffness. So if we were asked to compute the actual stiffness, we already had it because H1 is invariant to coordinate transformations. So H1 and H1 star are always equal. H2 star, well, by definition, it's equal to 0. So if we had done our calculations correctly. And H3 star is then the bending stiffness. So our H3 star is an integral, just like our H2. So it's E1. And then it's set minus set. So we're integrating again, of course, over two, having two contributions. One where we have our stiffness equal to E1, and we integrate with respect to z squared, but we need to remember to subtract our centroid here. So we're doing the calculations in the chosen coordinate system, and then we have to subtract our computed centroid in the formulas. Like this. Oh, apart from that, apart from this part of the equation, the calculations are much the same as for the H2. So that means that for our first one, our E1, well, we have 3a as the width, and then we can have the dz, and the limits are 2a, a to 2a. And then for the second part, we actually need two parts of it. The width of the first part is 3a. That's the part that goes from minus 2a to minus a. And then we have the second part. The middle part of the eye profile that only has the width a. And that's the one that goes from minus a to a. Putting all these things together, doing the calculations, we get H3 star equal to 163.15 EM A4. So in exercise 2, we're asked to compute the deflections, first at point B and then at point C. So this is an exercise in using the elementary cases. And can we still use the elementary cases even though we have a composite? Yes, if our bending stiffness is constant along the length. So we have computed H3 star, the bending stiffness, and it's constant. We have the constant cross-section along the length of the beam. So we can still use the elementary cases. Of course, we then just have to replace our deflections with, our bending stiffness, which H3 star. So, elementary case, we need, of course, to identify which elementary case it is. And in this case, we can see that it's the first one, so it's elementary case 1, right? But we need to use it repeatedly because we have two forces. So we can see here that our H3 star and then our deflection, and then we compute it at point B. So this quantity is what we find in the fifth column, right? That's in the elementary case, that's written EI W of X, but our EI is now H3 star, and we are finding the W of point B. So we just now need to, of course, identify the different contributions. So first we have the force F. Our length. Always be careful that you have the same length. And in some cases, the lengths are given in a different. It's like 2L for the entire beam, but here it's L, so it's easier. So it's L to the power of 3 divided by 6. And then we have all the contributions, beta, psi, stuff like this. We have now both the force acting. Now we're looking first at the force F. It's acting in the 1/3 point. So we have both alpha, beta is now 2/3. And our psi is 1/3, right? So we have 2/3. We have 1/3. And that means we have the parenthesis, which is 1 minus 4/9, which is 2/3 squared. And then we have minus 1/9, like this. And then we do not have the final contribution from this funny bracket, because that only is valid if our measurement point is larger than where, or is at a point to the right of the point where the force is placed. So in all of these cases, be very careful that you understand how to compute these different psi, beta, and this curly parenthesis. In this case, it vanishes. We also need the contribution from the second force. So the only difference here is that our beta is now equal to 1/3. We're still computing in the 1/3 point. So the second part will be like this. And all of this gives then 11 divided by 243 F times L cubed, right? And then we, of course, in order to find WB, we divide by H3 star. Now let's see what is the deflection at point C. Well, of course, we have the same formulas, but we just, again, need to be very careful of identifying the correct factors or the correct constants to put into the formula. So now we have, start again with the F. And our beta is the same. Now our psi is now 2/3. That means that we have 1 minus, and then we have 4/9 minus 4/9. And then in this case, the curly bracket is appearing because our psi is larger than our alpha. So we get plus, so our psi is 2/3. Our alpha is 1/3, and that should be cubed. Well, so really be careful that you remember this term if you compute this kind of expression. And then we have the second part here. Again, our psi is 2/3. Our beta, our beta is 1/3. Our psi is 2/3. 1 minus 1/9 minus 4/9. And in this case, the final bracket does not appear because psi is equal to alpha. A little bit confusing, but please make sure to rehearse this part because it's important to get the factors correct. And then we get 23 divided by 486 multiplied by FL cubed. Now in the final part of the exercise, we are asked to compute or calculate the numerically maximum effective stress in the material as well as the corresponding value in the fibers. Okay, so this is quite an extensive exercise here. So this requires quite a lot of work. One note about the two different values that we are asked to compute. So remember, it's probably better to write average stress here because that's what we mean. So remember, when you have a composite that's made of fiber and matrix material, then you have an average stress that you compute. But you can also identify the values in the fiber and in the matrix material. And so this is the fibers, which we are asked in the second case here. And why is that interesting? Of course, in principle, actually, the average stress is not that important because it just smears out the stress value. Usually, we have much higher values of the stress in the fibers than the average stress because the corresponding Young's modulus is higher. And so this is probably the most interesting, is to compute the stress in the fibers, because that's where we might have too high stresses that could correspond to failure in the material. But here we are asked about both the average stress, so seen as a composite, but also the value in the fibers. And we want to compute the maximum value. So that means we are both interested in computing where along the beam do we have the maximum stress, but also if we have it in the top and which part of the cross section. So there, you remember when you're asked about the maximum stress, it's both where along the beam, but also where in the cross section. Is it perhaps at the top part, or the bottom part, or is it the top part, or in between? And it's not in between, because we have the maximum strain either at the top or the bottom part, and therefore we usually also have the maximum stress at the top or the bottom part. So, and one thing to realize here is that when we're talking about maximum stress, it's at the point where we have the maximum moment, right? In this case, also, of course, normal forces from axial forces play a role, but here we have no axial forces. So the moment directly gives the stresses here, and so we have to compute and find where we have the maximum moment. And this is also a bit tedious here, because we have three different parts of our cross-section here, or our beam, where we need to do statics in order to find the moment distribution in three different parts here. So we need to make three cuts. And do statics in order to find the position of the maximum moment. So I'm going to jump a little bit ahead here doing that. I'm going to jump a little bit ahead. So making these three cuts and doing statics. First we have to find the support reactions. We don't know them, but we have a statically determinate system, so it's not difficult to find the support reactions in A and B. Then we do statics at the three cuts. And when we do that, so we see support reactions plus statics for three cuts. Then we get the following moment distribution. So in the first part, second part, like this. So I jumped, and I have just stated the conclusion. This is the moment distribution that we find from doing that. We already did similar calculations here in the repetition, the other repetition exercise. There is no specific need to repeat that, although of course it's very important. Remember, we want the maximum stress. We need to locate the position of the maximum moment. Doing that, we can just look at the function, and we find that the maximum moment is 5 divided by 9 F times L at x equal to 2L thirds. So at point C, we will have the maximum moment and we know the quantity now. Now we have the moment, and now we want to find the values of the stress. Let's first take a look at the strain, how the strain is actually distributed over the cross section. So we have computed the neutral axis for the centroid, elastic centroid, and that's of course the point where we have zero strain, right? So if we look, and that's the line here that I indicated with the dotted line here, that's the neutral axis for our cross section. This is our cross section with the stiff area down here. So if we look at the strain distributed, so we have here zero strain here, and then we have a linear distribution of strain up here, right? And if we look in the notes for the composites, we can find that the strain is computed. The strain is computed as our moment divided by our bending stiffness, which is of course in this case H3 star, and then multiplied by our distance from the neutral axis, so that we have a zero strain at the neutral axis, and then we have a positive strain if that is in some parts of the cross section, a negative strain in the other parts. So we're not specifically so interested in where we have positive or negative, but here we can see for this specific case that our beam is bending downwards, so we have a compression in the top fibers and we have tension in the bottom fiber. So actually we have positive down here in the bottom part and negative strains in the top part. So the parts where we have the maximum, numerical maximum, we have the maximum positive and maximum negative strains are on the top and bottom part. So we can say epsilon top and our set value. Remember, our set is still computed in the chosen coordinate system, right? So our set is minus 2a so we find the strain in the top part, and we find the strain in the bottom part. So we have the value of the strain in the top part, we have the value of the strain in the bottom part. So why are these relevant? Well, when we find the average stress, we find the value average stress top, we of course find by multiplying our strain with our Young's modulus. And our Young's modulus in the top part is E2. Right, because that's the average Young's modulus for the composite in the top. Two m, and this of course is the maximum moment, right? The max moment that we have computed. We are now at point C in the beam, looking at the cross section at point C. And if we get the average at the bottom, then we have E1, epsilon bottom. So what we can see here, actually, if we compute the values, is that even though our strain, the absolute value of our strain is larger at the top than it is at the bottom, because we are farther away or further away from our neutral axis, then because we have the higher E1 at the bottom, we actually have that the average stress is numerically larger at the bottom than at the top. Which is maybe a bit surprising. So we only can find this by actually finding both the value of the strain at the top and the bottom fiber, or a part of the cross section, and then multiplied by the corresponding Young's modulus at this part. So this is our average stress. But our fiber stress is of course found by having the strain multiplied by our fiber Young's modulus. And there, of course, we specifically know that the point where we have the largest strain is also the point where we have the largest fiber stress. So it will be E fiber multiplied by our epsilon top. And this is, of course, negative, so let's just take the numerical value like this. So we get here that the Young's modulus for the fibers were 35 EM. And then we have the epsilon top, which we have found, well, minus 2a minus ZC, and then we just take the numerical absolute value of here. So the key part to finding maximum stresses is finding the location of the moment where it's the biggest, and that was at point C along the beam, and then looking at the cross section first, identifying the strain at the top and the bottom, and we found that even though we had more strain at the top, the corresponding average stress was lower because of the lower Young's modulus. So the maximum average stress was at the bottom, but the maximum actual fiber stress was located at the top. So this is of course important for material failure. So this concludes this repetition session. 3 exercises done, covering actually quite a large part, specifically of the first part of the course, which is nice, which is maybe a little bit further away in your memory. Today we will, in the problem session today, we will do the exam from last year. Yes, so thank you for now.